So, to final part of the course on Poisson's equation. Now getting into time-dependent problems. So, as I mentioned previously, there's going to be one more homework besides what's been posted, and finally it's almost ready, and the notes to go with that. So. Probably in a few days, that'll be posted. Of course, you all have a bit more to get through on what already has been posted before we get to that. But so there'll be 9 homework problems in total. Hopefully, after you get through the first few, that it gets easier because a lot of these things are pretty similar, like these find difference approximations and such. So, okay.
Are you going to a STEM conference tomorrow?
What?
The STEM conference.
What about it?
Are you going?
Good question, because I have some other things going on during the day. Sarah's giving her perspectives tomorrow morning.
Yeah, sure.
Yeah, so I might have a chance to make an appearance. So we'll see. Yeah. I think it's like an all-day event or something
Yeah.
in a conference center, or
Mhm.
okay,
I don't know how long I'll stay, but I'll just go for a week.
okay, yeah, all right. Okay. All right. So for time-dependent problems. So we're looking at the PDEs of this form. So UDT is equal to some differential operator times U. And so you have the spatial domain omega, and then some interval in time from 0 to capital T. And then you have all right, so this is the difference between the PDE, we have the initial condition, and then we also have some boundary condition. Oh wait, some function, given function g of xt for x on the boundary of omega. Okay. All right. So all of this together constitutes an IBVP, so initial boundary value problem. Okay. Now, some examples of a differential operator L. Well, L, for instance, could be the Laplacian. So that would just give us the heat equation. All right, and then we have another possibility. LU is equal to, we've seen this equation before, the dot product of some given vector B with a gradient of U. So this is some kind of linear advection equation. It's basically wave propagation. Actually, those are kind of PDEs we'll see on the homework problems for this part. Okay, number one is LU is equal to minus the Laplacian of the Laplacian of U. So in other words, this is involving fourth order derivatives in space. So if UDT is equal to this, that's called the biharmonic equation. But if instead of UDT, if we have second derivative with respect to time, and this Laplacian squared, and that's called the beam equation. So that equation is that PDE is about the displacement of a beam. And of course, beams are not supposed to move very much. It's kind of very intense to stay stationary, but when a load is imposed on it, there's going to be some displacement. So in analyzing the integrity of structures, you want to have some idea of how much that beam could move under some kind of stress or strain. So beam equation is helpful for that. Okay, and one more. This is a nonlinear problem where you take the okay. Not sure if it's meant to be a the magnitude of the gradient of u. So that's going to be a nonlinear function of u. And this is for the Eikonal equation or the level set equation. Okay. The level set equation is useful for modeling interfaces between fluids. For example, this is useful for modeling and creating animations, like modeling the interface between water and air and how that changes over time in response to any like disturbances, like an object being dropped into the water. So the level set equation is used for that. In my notes, I had LU is equal to capital F times gradient U, and I'm not sure if it was meant to be like a function of the magnitude of the gradient, or F is some scaling constant, and in which case, why bother having it? So that's something I'll have to check on. Okay. Now, so the time independent PDEs that we've seen, like Poisson's equation, can be thought of as the steady state versions of these PDEs. For example, if I take the heat equation, so UT equals Laplacian of U, and then I consider a steady state version of that, that's where you set any time derivative is equal to 0, and then Laplace's equation pops out. Or if I have du dt is equal to Lu plus F, where L is the Laplacian, and again I set du dt equal to 0, then I have Laplacian of U plus F is equal to 0. That's Poisson's equation. So so that's where a lot of important time-independent PDEs come from. It's just from considering a steady state setting for time-dependent ones. Like to get an idea of, is a solution supposed to converge to something over time? And the steady state version of a PDE can give you an idea of what that is. Okay. All right. Any questions about sort of tiptoeing into this? Okay. So, as I've already mentioned with beam equation, so not all time-dependent PDEs are first order in time. So as an example, the wave equation. So UTT equal to UXX in one dimension, one space dimension. However, if you do have a higher order derivative in time, like this, use the fact that any like higher order ODE can be written as a system of first order ODEs. So we can rewrite as first order system. So for a purpose of numerical solution, we can assume that any PDE you're dealing with is first order in time. It might be a system instead of a single equation. So an example of that with this wave equation right here, you can do UDT is equal to dvdx, and then dvdt is equal to udx. All right, so because then if I take the derivative of this equation with respect to t, I get dtx. But then if I take the derivative of this equation with respect to x, I get dxt is equal to uxx. So then I get utt equals uxx. So these two are equivalent. So there's no loss in generality on focusing on PDEs in the form like first derivative with respect to time is equal to something. All right. Now, so when you have a PDE that has both space and time in it, there are different approaches to discretization. So if you have some initial boundary value problem, here are two approaches that you can take. All right. So the first approach, which I think is the most commonly used, is called the method of lines. And in the method of lines, the idea is you discretize in space first. So if we look at a generic PDE, so UDT is equal to LU, you discretize that in space, and you get U prime is equal to AU, where now we have U as a vector. So it's a vector valued function of time. So UT is equal to a vector of components U of x1t, U of x2t, and so on. And so it has the values of your solution at that particular time and all of the points on your spatial grid from discretizing in space. So your PDE is now approximated by a system of ODEs. And now you can use whatever methods are available to solve that system of ODEs on various time-stepping methods, which is what I'm going to focus on during this entire chapter. Okay. So that's one approach. The other approach doesn't really have a fancy name to go with it. Basically, discretize in time first. So what you have is, so UT equals LU becomes, replace the time derivative with a finite difference. Okay. So now you can think of this equation here as some kind of time independent, still a PDE, where any time derivatives are gone, but spatial derivatives remain. So what you can do is you can think of u of x t plus delta t as the unknown. U of x t is now known, and now you're solving for that. Right. So at each time step, what you're doing is you're solving a stationary steady state problem. Okay. Now, from this point on, we're going to focus on the first approach. So we assume that we have some PDE, we discretize in space, we have a system of ODEs. So now I'm going to spend the rest of the time talking about if you have some ODE, really whatever or system of ODEs, whether it came from a PDE or not, what are some time-stepping methods that we can use to try to solve that? Okay. So our generic system of ODEs we're not going to solve is y prime f p y. So we assume that y is a vector, possibly. So therefore, the time derivative f is a vector value function. And then we'll have some kind of initial condition. Okay. So for any problem with this form, how do we go about solving it? what we do is we use time stepping, also known as time marching. And what we do is we will actually compute our solution at discrete times. So use this notation, yn is our approximation of the exact solution y at some time tn, and tn equal to n times delta t. So delta t is our time step size. So we're gonna, we start with our initial condition at t equals 0, and we're going to compute solutions at t equals delta t, 2 delta t, 3 delta t, and so on. Now, here I'm using a uniform time step, delta t. There are ways to adjust the time step. It's called adaptive time stepping. I'm not really going to get into that, but that is a thing. But for simplicity, we're just going to assume that we're using a uniform time step to compute the solution at equally spaced times. All right. So, I'm going to mention two of the simplest time stepping methods. Both named after our most mispronounced mathematician, Euler, opposed to Euler. Okay, so we have forward Euler, also known as explicit Euler. So all we do is you replace the time derivative, y prime, with a forward difference. So y prime at Tn is approximated by y of Tn plus delta t minus y of Tn over delta c. And then that is approximately equal to f at Tn y of Tn. So, because y prime of Tn is supposed to be exactly equal to f of Tn y of Tn. So that leads to this. So if I take this method and rearrange it to solve for y at the new time, I get this method. Yn plus 1 is equal to yn plus delta t f at Tn yn. So this is the actual explicit Euler method.
Yn is nothing but y at t.
Yeah, so keep in mind, this refers to the computed solution. When it's y of t, that's the exact. Yeah. And this will be important for any error analysis that we do. Okay. The other method is the opposite in a sense. So it's the backward Euler. Also known as implicit Euler. So what we do in this case is we approximate the time derivative at Tn plus 1 by a backward difference. So notice the expression that I have here and here are exactly the same, but they're used differently. They're meant to approximate the time derivative at a different time. Tn here, Tn plus 1 here. And then this is approximately equated to f at Tn plus 1. Okay. So we're using Tn plus 1 as the center of, you can think of this as using a Taylor approximation to approximate the derivative. Okay, but here the center is Tn, here the center is Tn plus 1. So now if I rearrange this to again solve for y at the new time, then I get the actual formula for backward Euler, and it looks very similar to forward Euler. The only difference is where the time derivative f is evaluated. So for forward Euler, it's evaluated at time Tn. Here it's at time Tn plus 1. Okay. Now, here we have yn plus 1 appearing on both. And that's what you're trying to compute. So what you have to do is you have to solve this equation for yn plus 1. For example, you can use some sort of root finding method to solve by iteration. You could use like fixed point iteration, or you could try using Newton's method, something like that. So what that means is, so this is the case for all implicit methods. So forward Euler is an example of an explicit method where you can just basically plug and chug everything on the right side to get the new value on the left side. An implicit method, the new value yn plus 1 is implicitly defined by this equation, which you now have to solve for yn plus 1. So it's like the difference between an explicit function and an implicit function. So generally time-stepping methods fall into one of these categories, for either explicit or implicit. And you can see from this example here that if I need to use some iteration to get yn plus 1, that an implicit method is a lot more work per time step than an explicit method. That's not always true. It really just depends on the problem. Like if f is a particularly simple function, like what if f is a multiplication by a sparse matrix? Okay, but you have to solve a system of equations, but that could actually be done really efficiently. So, but in most cases, it is true that an implicit method requires more work. But I want to emphasize this per time step. And that becomes an important distinction, as we'll see later, that in some cases, one of the drawbacks of explicit methods, per time step, the work is simpler, but you may have to take more time steps. You might need to use a much smaller delta t with an explicit method than an implicit method. So that makes up for it. So implicit methods are actually very widely used, at least for certain problems. Because the way an initial boundary value problem is defined, you start at time 0, and then you're trying to get to some final time, and you're taking some steps to get there. If you had to use a smaller delta t, then you got to take more steps because you're still trying to get to the same place in the end. Is there any questions about the general descriptions of these methods? Yeah.
So, are there situations where we are compelled to use a particular method?
Sorry, what?
Are there situations
Yeah.
where we are supposed to use a particular method, either the explicit or the implicit?
Okay, so. Yeah, so different problems, like generally you have a lot of choice when it comes to what methods you use. But there are some methods for which for some problems for which certain methods are a much better idea. So as an example, if you're solving a wave equation, like an advective problem, you can do pretty well with either explicit or implicit. But if you've problems where you have a lot of exponential behavior, like for example, heat equation, where you have exponential decay, or the beam equation, which is even more stringent because you have those higher order time derivatives. So problems with higher order time derivatives generally favor to use implicit methods because the higher order of spatial derivative you have, generally the smaller time step you must use. Because when you take if you're dividing a matrix to represent like a spatial derivative, say the second derivative, you got to divide by delta x squared. And dividing by delta x squared makes that matrix really large. So then you got to use a small time step to compensate for it. So, so the conventional wisdom is higher order spatial derivative methods, you're better off with implicit. What I've seen is that if you ever want to code your time-stepping method yourself instead of using some off-the-shelf thing, you might find you prefer to code up an explicit method just because it's so much easier. And then, okay, then you got to use a small time step, but if you don't care about just letting the computer just run forever to get a solution, then you might not care about that. I mean, my research is about designing time-stepping methods that work a whole lot faster for those people who do care about that, which is not everybody. But yeah, over the coming classes, I'll be introducing various categories of time-stepping methods, and then we'll talk about their advantages and disadvantages. And there's a lot of choice there. Okay. All right. Now, during the remainder of the time, what I'll do is I'll pick out the simplest method, forward Euler, and show you how to do convergence analysis. Now we saw convergence analysis before, where for Poisson's equation for like a finite difference method, you're solving AU equals F system of equations, and there we learned about local truncation error and establishing like stability and convergence. So all those same error analysis concepts, consistency, stability, convergence, apply equally well to time-dependent problems too. You just have to have the right definitions of these concepts for this setting. Okay, so first, read back a concept of local truncation error. So LTE. Now, the general definition of local truncation error is actually the same as for time-independent problems. What you do is you substitute the exact solution into the numerical method. Now, a computed solution that is generated by the numerical method satisfies the numerical method exactly. The exact solution will not. It's going to be something left over. That something is a local truncation error. Okay. So, and a way we can get a hold of an expression for local truncation error is Taylor expansion, which is the same thing as we saw before. Okay. So for explicit Euler, to get the local truncation error, call it tau n. This can be a vector. What I do is for time-stepping methods, it's important to write the method in a way that is consistent with the ODE. So in this case, so for explicit Euler, which I'll repeat it here, yn plus 1 is equal to yn plus delta t f tn yn. So I'm going to rewrite this so that we can see the approximation of dy dt. Now I have my approximation of dy dt minus f. Okay, so this is Euler's method rearranged to correspond to the ODE of solving y prime minus f equals 0. All right. So what I can do is take a Taylor expansion. And I can take my expansion around Tn. So if I do that and I go out to the second derivative term, then I won't go through all the mechanics here, but basically a lot of simplification will happen. Because the first term of my Taylor expansion will be y of Tn. Oh, yeah, I'll just write it down. Not that much. So y of Tn plus delta t y prime of Tn plus 1/2 delta t squared y double prime at some unknown point. Now y prime, that's equal to f. And Cn is some unknown point that lies between Tn plus 1. So if I substitute this Taylor expansion in here, well, we see y of Tn's are going to cancel out. And then this term is going to cancel out also. So a local truncation error turns out to be, okay, yeah, delta t over 2, y double prime. Oh, divided by delta t, yeah. Okay. Oh, a mistake here in the notes. I have the error is order h, but I'm not using h to refer to spacing. It's delta t. Whoops. Okay. All right. So because the error is the local truncation error is proportional to delta t to the first power, the big O of delta t, we say that explicit Euler is, or forward Euler, is first order accurate. Okay. So not great, but I mean, it's such a simple method. What do you expect? And if I were to carry this out for implicit Euler or backward Euler, I would pretty much get the same result. The only difference is the error would be the opposite sign. But so it's also first order accurate. So that's how we get local truncation error for time dependent case. All right, so any questions about that? Okay. So now the last thing to do is try to get a handle on global truncation error. And that is analogous to what we saw for time independent problems also. All righty. But for global truncation error, so GTE, that's what we really care about. The actual difference between the exact solution and computed solution at any time it's on the grid. So exact solution minus computed solution. Okay. Now, so if I write out what we have going on for the both exact and computed solutions, well, we have y of tn plus 1. It is y of tn plus delta t f at tn y of tn. And then I add on delta t times the local truncation error, Tn. So when you plug in your exact solution into your method, you get the same thing as the description of the method, except you have to add on the term delta t. Do not forget the factor of delta t times the local truncation error. And then the computed solution, one is yn plus delta t f n yn. And then there's no, then the computed solution satisfies the numerical method exactly, so there's no truncation error term. So now what I can do is I can subtract these and use my definition of global truncation error. And I get E n plus 1 equal to vector, so E n plus delta t. Now these f's are evaluated at different times. We're going to have to deal with that. So the times are the same, but the y values are different. And then still have its global truncation error. Now, we're going to make an assumption. It's a standard assumption for like its existence uniqueness theory of ODEs, we'll assume that the function from the ODE f is Lipschitz continuous in the y variable. So what that means is, you evaluate f at the same time value with different y values that is less than or equal to some constant that's called a Lipschitz constant times the difference of the y values. So basically, it's a way of saying that the function is continuous, although it's actually a stronger form of continuity than just plain continuity. Because it also would imply if f is differentiable, that the derivatives are bounded. Okay. So that means this difference of f values is magnitude is less or equal to the Lipschitz constant times the difference of these y values. So if I take the norm of both sides, I get En plus 1 norm is less than or equal to, and then I get 1 plus delta T L, the Lipschitz constant, times the norm of En. So the delta T L times En comes from applying the Lipschitz condition to this difference of f values. That is y of Tn minus Yn, that's En. And then we still have a local truncation error term. Got to take the norm of that too. So at least we have a bound, an upper bound on the size of the new error in terms of the old error.
En plus 1 will be the
Yeah, that's the new error. Yeah. So now what I can do is I can apply this, basically I have a recurrence. Shows how En plus 1 depends on En. So I can apply that relationship repeatedly. So if I use this to express En in terms of En minus 1, I have so then I would end up with, if I simplify this, I have 1 plus delta T L squared En minus 1. And then I have plus delta T times 1 plus delta L tau n minus 1 plus plain tau n. Okay. Now I can apply this recurrence again to En minus one to get En minus two. So I'm gonna get a higher power of one plus delta T L out here. And then I'm gonna have each truncation error multiplied by some power of one plus delta T. Oh, whoops, that's wrong. Delta T L. One plus delta T L. Okay. So I could keep doing this to go all the way back to E0 and see what expression I get for the global error in that case. So if I were to keep doing that, first, any questions about this before I show you? Okay, yeah. Okay. Okay. All right. So then this is what I end up with is a way to express. What I want is a closed form expression for the error at any time, not depending on previous errors. So I guess you think of it as like solving the recurrence relation. All right. So what I get is En north is less than or equal to, I get 1 plus delta T L to the N E0, so the error in the initial data, plus delta T times the sum of the powers of 1 plus delta TL times different local truncation errors. Yeah. Oh. Something wrong here. Oh.
I'm getting it.
What?
Summation of sorry. Summation of L delta T to the power.
Well, are you expanding this?
Yes.
Don't.
No, I did it in previous.
Oh.
Yeah, that's what I was thinking. That's why I was waiting on a computer.
Oh, okay. Oh, I think I have a mistake here. It should be n minus I, not I. Because for instance, what I've written up previously, I had 1 plus delta TL to the first power times tau n minus 1. But tau n had no factor of 1 plus delta TL. Now, it's not going to affect my final result, thankfully, but this intermediate step is off.
What I was trying to do was I was trying to match the power of delta TL separately.
Oh, okay.
With a different TN, so I've just
Oh,
only two different terms.
oh, okay.
One in terms of summation of delta, the other in delta.
Oh, okay. Oops. Alright. Okay. Alright. Now, here we have different local truncation errors, but they all have the same form. Okay, so first remember, tau I is equal to delta t over 2 times y double prime at some unknown point. So what I'm going to do is, I'm going to let capital M be the maximum over my entire domain in time of the magnitude of y double prime of t. So we're assuming that y double prime is continuous. In other words, we're assuming y is twice continuously differentiable on this domain. So we do need that. So we need to guarantee that there is a maximum, because a continuous function on a closed interval has a maximum. Okay. Got those in mind. Okay, so then I did say that the local truncation error is less than or equal to delta t over 2 times m. The reason I'm doing that is here I have, these are different local truncation errors, so I cannot factor this out with sum. But by replacing this with an upper bound that is independent of I, now I can factor that out. Also, this is 0, because E0 is the difference between the exact solution and computed solution at time 0, but at time 0, we're just using the initial data. So there isn't any error at the outset. But it is a little sloppy because we probably should assume some sort of rounding error, but we're not going to bother with that. So this term's gone. So now what we have, less or equal to delta t, and then my bound in the local truncation error, so that's delta t m over 2. And then I have this sum of these powers of 1 plus delta t L. Now this is a partial sum of a geometric series. There's a formula for that. Now I have delta t squared m over 2. So the formula for this is, we're going from powers from 0 up to n minus 1. So this is 1 plus delta t L to the n minus 1 over 1 plus delta t L minus 1. But the denominator just simplifies to delta t, which will cancel with one of the delta t's up here. So this is less than or equal to delta t m over 2. Then we have 1 plus delta t L to the n minus 1. Okay. Now, 1 plus delta TL, that is the first two terms of a Taylor expansion of e to the L delta t. So I can replace it by this. Now I have e to the L delta t n minus 1. But delta t times n, that is equal to t sub n. T,
Piece of it.
yeah, because t sub n is defined to be n times delta t. Yeah. But Tn is limited to the domain from 0 to capital T. So this is bounded further by delta T m over 2 e to the L capital T minus 1. So now the error is bounded by delta T times something that is completely independent of delta T. Like I said, this is big O of delta T. And that tells me that the error goes to 0 as delta T goes to 0. So from there, I can finally conclude that forward Euler is convergent. That's what you need. You need to show that the global truncation error at any time in your domain goes to 0 as delta T goes to 0. And now we have. Yes. And because it's delta T to the first power, that's how we know that it is first order accurate. We already know that forward Euler is first order accurate locally, but now we see that it's true globally too. And that's actually why we define the local truncation error in the way that we do, by rearranging the method a little bit, so that the order of accuracy locally and globally are the same.
So I need to.
Okay, well, actually, pretty much done anyway, so, yeah. Yeah, I actually have reached the end of my notes. All right, yeah. Okay,
Why did you replace T sub n by T?
oh, just to get an upper bound. I guess you didn't absolutely have to do that, but at least this way, because what you want is, you want to show your error is some power of delta T times a constant. And here, this still depended on the individual times. So we just want to get that out of the picture. Yeah. Now, this is an extremely crude or coarse upper bound. Like if you went ahead and applied forward Euler to a certain problem, and for which you know the exact solution to compute the error, it's going to be a much less than this. But we're just trying to show convergence. Dang it. Well, you're a little left. Do you have any more questions?
No.
All more questions?
Just started working on question 4.
Okay, well, that's good progress. That's for somebody. So, yeah, okay. All right, I guess that's it then. Yeah. Okay.
Thank you.
Yep.